Excellent. So my name is Thorsten Löffler from ETH Zurich from the Scalable Parallel Computing Lab, and I'm super happy to kick off this year's SPCL BCast series with a wonderful speaker, Petar Veličković, who was planning to tell us about algorithmic alignment, but in the last moment changed his title to monoids, actually something very close to my heart as well, and graph neural networks. So Patrick will introduce the speaker formally, and I'm very happy to have Petar. Thank you, Petar.
Thanks for having me.
Thank you. Petar is a staff research scientist at Google DeepMind, an affiliated lecturer at the University of Cambridge, and an associate of Clare Hall, Cambridge. He holds a PhD in computer science from the University of Cambridge, Trinity College. His research concerns geometric deep learning, a topic he's co-written a proto-book about. For his contributions, he's recognized as an Alice Scholar in the Geometric Deep Learning program. Particularly, he focuses on graph representation learning and its applications in algorithmic reasoning. He's the first author of Graph Attention Networks, a popular convolutional layer for graphs, and Deep Graph Infomax, a popular self-supervised learning pipeline for graphs. His research has been used in improving travel time predictions in Google Maps and guiding the intuitions of mathematicians towards new top-tier theorems and conjectures. Without further ado, the stage is all yours, Petar.
Thanks, Patrick, for the fine introduction. I will just add, and this week also using graph machine learning to improve football tactics, which is a paper we released with Liverpool Football Club a few days ago, but I haven't updated my biography yet. Yeah, and thanks so much, Thorsten, for having me. I will say that while the title doesn't have algorithmic alignment in it, I'm still very much going to be talking about algorithmic alignment. It just turns out you cannot talk about this without talking about monoids, and I felt, why skip the good stuff? Let's just dive into what the good stuff is, right? So, as you can see from the title, we'll be talking about different aspects of time and synchronicity inside neural networks. Well, primarily graph neural networks, but you'll hopefully see very quickly why I've chosen to focus on graph neural networks here. And we will see how to focus on these things. It is going to be very useful to consider a monoidal framework. As mentioned, my name is Petar Veličković. I'm a staff researcher at Google DeepMind and the University of Cambridge, where I'm an affiliate lecturer. And it is a great pleasure to be here, albeit virtually, but I do hope that I'll have more opportunities to interact with this group of people in person. So just to set the stage, in this talk, we will be discussing classical computation. When I say classical computation, I mean the kinds of things you would typically see in an undergraduate course on algorithms or data structures. So hopefully, to those of you with a computer science background, this will look fairly familiar. These are all shots from the Introduction to Algorithms textbook, and they cover various aspects of things like sorting, searching, pathfinding, various clever ways to solve problems and organize data in a way that is more efficient. And because there is a deep learning connotation to the seminar, we will also be discussing how to take this computation and capture it inside a neural network. So this is going to be kind of the broad strokes topic that I'm going to be interested in for the talk today. And maybe before we dive into the specifics of how we can do this, and also how monoids come into play and how time and synchronicity come into play, I would like to actually take a step back, because I imagine some of the people in this group haven't necessarily been familiar with some of my recent research, or maybe even, it's not necessarily clear from this research where I want to take all of this. So I felt like it would be useful to set the stage and also to get you motivated for the things I'm going to talk about today, to tell you just a little bit about what I want out of all of this. Like, why do I care about all of these things? And what I want is robust reasoning in neural networks. This is really the thing that's important to me. And so the key aim for me is this keyword, reasoning. The problem is when you start talking about reasoning, especially in today's day and age, you'll end up with 100 people with 100 different opinions. So let me make it very clear what at least myself and my team at Google DeepMind that works with me on these things has agreed as a sort of operational definition of reasoning. So to me, reasoning is a robust procedure that can solve instances of problems. This is really the key word. It's the robust. It's not the solving. It's not the instances. It's not the problem. It's the robustness part. And so what I mean by this, I don't mean when I say robust, I don't mean you should always give me a 100% accurate output. In fact, I would argue humans do reasoning, and human reasoning is often not 100% accurate. So humans might try to follow an algorithm, but might fail to follow it in some parts, or they might not have complete data to follow it in some parts. So imperfections are not a problem for me. And also, some people think about reasoning as something that takes place purely in a symbolic space, manipulating kind of base ground objects. I think that's potentially useful, but I don't require it to be explicit or symbolic. Reasoning could also take place fully in a high-dimensional latent space, and I'm also totally happy about that, especially with the advent of deep learning architectures. But the thing I do want out of a system that claims to be reasoning is that it behaves in a consistent manner across all problem instances I give it. So it might do things wrong, but it might be able to give me some correctness bound or some prediction of how accurate it's going to be when I apply it to large enough inputs, or even if it completely gives up to give an answer when I give it an input that's too big for its current algorithmic capabilities, I would also consider that to be a good instance of reasoning. Current state-of-the-art frontier models, as you might know, are not trained to do this. They are trained to try to give you an answer, even if they have no chance whatsoever of giving you a correct answer. And that obviously is not a sign of understanding what it needs to do. So really what we care about here is out-of-distribution generalization. Why do I say this? Because if you train on a data set which contains what you want inside its training distribution, the instances of the problems you care about, then your system can solve it just by clever association. But how well does it generalize to examples outside of the distribution you've trained it on are actually the examples on which you can test, does it truly understand the computational procedure that's enveloped inside this reasoning? So to maybe put it in very blunt layman's terms, which is also a brutal example I tend to give these days, a model that truly captures the concept of multiplication, right, the very standard arithmetic algorithm, should work equally well, or at least predict how much it's going to be wrong on all instances of multiplication problems. And why do I consider this to be an important motivational example? Because basically transformers compute billions, hundreds of billions of multiplications just to generate a single token, but they cannot reliably multiply 3-by-3 digit numbers accurately, right? And this is a table, this is a very standard heat map that generalizes across all of the current frontier models. So Gemini Ultra, GPT-4, there's several references you can see for some of our state-of-the-art models. They compute lots of multiplications, but they cannot reliably multiply. So I cannot claim that this system has understood the concept of multiplication, unfortunately. And this is just a simple example. You can imagine how when algorithms that you want to execute or problems you want to solve get more complicated, the capabilities of these models get equally more strained. Further, I don't just want to, and this is maybe one thing that's specific to my approach to the problem, which might inform some of the decisions I make later on, is I don't want to just do this in a way that like solves the problem in theory, but then I cannot actually build anything practical out of it. I would like to be able to solve out-of-distribution generalization in a way that will scale to 100 billions of parameters and things like that, right? Like I would like to be able to build scalable, practical, large models that have these reasoning capabilities baked into them. So this means that some approaches that might work really well, but are, say, exponential time complexity or not easy to pack in memory, would not be applicable for what I want to do. Now, you pitch this kind of approach to people who are currently in the scaling maximalist camp, and you get typically two kinds of responses. One response is you can solve this kind of reasoning just by gathering more targeted training data. And while this is certainly true for certain kinds of products you want to build, if you want to solve true out-of-distribution reasoning, data alone is unlikely to be enough. And we've known about this in many ways and forms for several years now. This is just one reference that I like to give because it's such a beautiful geometric argument that makes it very obvious why just by adding more training data, you're not going to solve out-of-distribution by itself. And specifically in this great paper from researchers from MIT on how neural networks extrapolate, they studied specifically ReLU-MLPs, which is a particular popular class of neural network priors. But also, as you probably know, if you have a ReLU activation function in your multilayer perceptron, it's going to be basically a piecewise linear function, right? So as you move away enough from the training data support, you are going to hit that pure linear regime. And at that point, unless your target function is linear, you have zero chance of extrapolating correctly. And here I've shown you just 4 kind of very obvious geometric examples that these guys have drawn in their paper, where you try to fit a ReLU-MLP on a data set of points. The blue points are the training set. And you can see how they fit really well the training set, but then outside of the training set, they quickly converge to the purely linear regime and fail drastically to model the target function. And one of the main contributions of this paper is not so much that they discovered this effect, like this is a very kind of obvious consequence of piecewise linear functions, but these guys have been able to prove that actually not only will it converge to a purely linear regime, it will converge really, really fast to that linear regime as you go away from the support of the training set. The convergence rate is very fast. So it's not just that this is an effect that will happen far enough from the training set. It actually happens already at small amounts of far away from the training set. So basically just adding more data will help you generalize in those regions, but will not help you generalize outside of the regions of what the data can support. So unfortunate, but there we are. And there's been, by the way, many recent extensions that deal with this variant of this question even outside of ReLU-MLPs, because obviously this exact argument only works when you have a piecewise linear function. Nowadays in deep learning, ReLUs are still popular, but we're slowly replacing them with novel variants that are smooth and not piecewise linear. So basically, the exact findings of this theorem do not hold. However, there have been extensions, and the work of Veličković and also the work I've done together with Andrew Dudzik show 2 directions of how we can use theories of causal reasoning as well as category theory to explain some further aspects of why data alone will not solve this problem. The second response you might typically get, and I'm sure some of you were eager to ask me this question during the Q&A, is why not just attach a tool or make the model write code? And in this way, we don't have the problems of generalization that the model itself might have, which is a fair argument. Obviously, if you hook up the output of your neural network to some fixed tools, plugins, or algorithms, you will have basically removed the fundamental constraint of this problem, which is now you will have a component that trivially generalizes out of distribution to any input you give it, the tool itself. However, and by the way, this type of research has been done for many years in the neurosymbolic community. It's just become very popularized nowadays in the context of transformers. The tool former paper is maybe one of the first really popularizing examples that I'm aware of. And as I said, clearly this doesn't have the out-of-distribution issues of neural networks because it has this tool component, which can be verified and robust. However, if you just do this, you are admitting defeat before even starting, because the whole success of this fragile system depends on the neural network giving the correct inputs for your tool. So if your neural network isn't capable enough to extract the right inputs, then you'll be back where you started. In fact, you might be in a worse position because the tool will take the wrong inputs, happily give you wrong outputs, and then those wrong outputs will condition everything that happens in the future. So this is a problem. And sometimes the act of extracting correct inputs might itself require a reasoning procedure. So you're not escaping reasoning inside the model by just offloading some of it to the tool. So if you just decide to use a tool, you're acknowledging the neural net cannot do this, and you're committing yourself to the outputs of the tool, even if there are any errors. So I don't think we should accept the status quo. Like, tools are going to be really useful. I think we're definitely going to keep using them. They're here to stay. But we can definitely see if we can make the neural network itself a little bit more tool-like. So my conclusion is we likely need to change the equations of the model in order to capture computation better, because data will not be enough, and slapping on tools will likely also not be enough in the current state of affairs. In order to be able to talk about how to change the model equations, I need to introduce the model itself to you. So this will take a little bit of our time to cover just a few preliminaries. This will be quite familiar to those of you who have done stuff with graphs before, but I feel like it's important even for those people, because I might use a slightly different notation to what you're used to. So just to make you comfortable with the notation I'm using, I'm going to kind of start from the basics and go from there. So first of all, before we dive into the model itself, let's talk a bit about how do we even evaluate to what extent the model generalizes out of distribution. I would actually argue, especially in the day and age of large language models trained on the entire internet, most of the popular benchmarks are unsuitable for this because you have distribution leakage. There's very little chance that there isn't a corner on the internet where someone might have tried to do the same thing that you're asking in your Q&A data set, right? So we need tasks for which we can generate outputs reliably. So we need correct outputs. Efficiently, so we need to make sure that we can generate for any input we want and that it will terminate on time, produce the right answer. To be honest, when you collect all of these constraints together, this is basically polynomial time algorithms. Like, that is the thing that fits all of this criteria. It is efficient because it's computable in polynomial time. It can give us output for any valid distribution of interest, and it is reliable. If we have a correct algorithm for a certain problem, we can generate entire traces that match that algorithm. Here you have one example of what such a trace might look like for a classical sorting algorithm, insertion sort. You can see all 5 steps of the sorting algorithm are represented, where it gradually slots one item at a time at its place, and it rewires the edges of this list. So it starts from a list 5, 2, 4, 3, 1, and gradually goes towards list 1, 2, 3, 4, 5, right? And this is something that I knew from way before large language models became a thing. I knew that this was going to be important. And there wasn't really a proper data set for people in machine learning to use to evaluate these things. So every single paper that looked at algorithmic generalization had to define its own data set, and it was basically impossible to track progress across different papers. And this prompted me to propose what is now known as the CLRS 30 benchmark. This was, by the way, a 2.5-year engineering effort where I basically, worked really hard to try to go through the textbook on algorithms that is now standard in most undergraduate courses, the Introduction to Algorithm textbook, and just basically look through it, look at the different classes of algorithms that are in there, and try to convert all of them into a common representation so I can create a data set of execution traces that we can train machine learning models on, right? This was an effort that lasted quite a long time, but it was quite fruitful. And now we have a data set of 30 different algorithms across 8 different types of computation. So sorting, searching, pathfinding, dynamic programming, geometric algorithms, as well as string matching. So all of it is covered inside this one data set. And I should also stress that it is not just a data set, right? Because it's an algorithm, it can generate data for you of any input you want, as long as that input is valid input for that particular algorithm. And also, once you have generated your data, there is an automatic knowledge of what your encoder and decoder functions should look like and what your loss functions should look like if you want to match the trace of that algorithm. So I like to say that CLRS 30 is not just a single data set, it's a data set and baseline generator, because it allows you to specify polynomial time algorithms. And then once you have the right specifiers and the data samplers, it takes care of everything else for you. It generates the machine learning models, it generates the batching logic, it generates the loss functions, it generates the whole training loop that you can use to train these models. So you don't have to worry about anything other than specifying an algorithm and maybe specifying the architecture of the processor network that kind of deals with the data latently. The library takes care of everything else. And that's part of the reason why it took 2.5 years to build, because it really unified all of these things under a common representation. This is work we published at ICML, and I'm very proud that it is work that we open sourced. So we can find it on Google DeepMind's GitHub, publicly available. Please feel free to play with it. I've personally worked on it for 2.5 years. I can help out if you need any assistance, but I do think that this is the benchmark framework that we should use for out-of-distribution generalization evaluation. Now, that was about data. We also need to talk about models, so we can talk about modifying their equations. And specifically, the model that we're going to use is the graph neural network, or GNN model. And it's a fairly general model, which is well aligned with various forms of computation. We'll see this in a few slides' time. So basically, I felt that it would be a pretty good target for the algorithmic investigation we want to do here. And if you're not familiar with graph neural networks, I'll just quickly explain them. Basically, they rely on this local message passing mechanism where you have nodes in a graph. Each node has a feature vector xu attached to that particular node. And you want to use those feature vectors and the edges in the graph to update the representations of nodes in some higher dimensional space. And the way it works is along each edge of the graph, the two nodes collaborate to compute a message vector, m, which is sent across that edge. And there is this message function psi, which computes the message, right? So it takes into account the features of the two nodes and computes a vector message to be sent across. Then, once all of the messages are computed, the receiver node aggregates all of those messages together using this aggregation function big O plus. And it's something that just converts a bag or multi-set of message vectors into a single aggregated vector. For those of you who like monoids, you will immediately see that this is the same as choosing a monoid structure on R to the M, because this aggregation function needs to be invariant to permutations. So it needs to, like for this to be a valid graph neural network, it needs to give me the same answer, even if I permute the order in which I present the neighbors to you. So this is often realized as a commutative monoid. And finally, once all the messages are aggregated, the node can update its representations in some latent space H through the use of an update function, which takes the features that that node used to have, the aggregated messages, and then updates those to a new space, right? So these three parts are what make up a GNN. This function is applied kind of in parallel to every single node's neighborhood. And the message and update functions are the only learnable parts of this model. Everything else is just data flow specified by the shape of the graph. And you might imagine the psi and phi functions to just be some single layer neural networks or maybe deeper neural networks. And you can optimize their parameters through gradient descent as you normally would, because all of this is differentiable in all of the inputs. Now, as I said, this graph neural network idea is a remarkably general idea. I don't know how obvious it is, but you can express transformers using this paradigm. Just replace your message function with a value computation and your aggregation function with an attention mechanism. And you can basically see how its tokens talking to each other effectively in a fully connected graph structure. So this is a very generic model and one that maybe is even more expressive, but a bit less scalable than a transformer. And as a result, we use it just because it gives us maximal power when deciding how to align these computations. Now, those of you who know about my research output will know that I am a big fan of GNNs. I've worked on them for a very long time. But basically, this is something I've talked about and thought about for a very long time. And therefore, I've written about it and talked about it a lot more. Unfortunately, I don't have time in this talk to talk more about GNNs. However, if you want to learn more about GNNs and you want some resources to do that, I'd say great places to start are the position paper on Everything is Connected, which I published in a journal some time ago, and the talk on theoretical foundations of GNNs, which I have put on YouTube. It's publicly available. It already has about 70,000 views, so it's reasonably popular. And even though it's a bit old by today's standards, I would say it still has the right kinds of pointers for getting started in the field. But now let's talk a little bit about what I actually do, right? So I've introduced the preliminaries, what kind of data I train on to ascertain out-of-distribution generalization, what kind of models I build. Now let's see how I can try to capture computation inside those models. And realistically, what I do is I try to do this algorithmic alignment game. And the key concept here is that for those of you who are familiar with classical algorithms, you might know some of these classical path-finding approaches like the Bellman-Ford algorithm, which compute the distances to every single node in a graph by basically a clever local update rule that takes the distance to a particular node as the minimum of distance to reach a neighbor plus traveling the edge from the neighbor to the node itself. And now this is a rule you can apply repeatedly in every single node, and eventually it will converge to the correct answer if you initialize it properly with distance 0 in the source and distance infinity everywhere else, right? And one thing that you might want to notice here is that this algorithm looks very much like that message passing equation I just showed you, right? Because you can imagine the distance variables as the node features in a graph. You can imagine the act of adding the edge weight as computing a message function along that edge. And you can imagine computing the optimal neighbor as an aggregation function over all of the neighbors, right? So every single part of this algorithm can be decomposed in a way that it matches very nicely parts of the message passing equation. And this is the idea of algorithmic alignment. You're trying to cut up your neural network into parts and line up those parts with different parts of a target computation you might want to execute. And this is actually a really powerful idea, because using it, we can actually mathematically formalize what does it mean for an architecture, a neural network type, to be better or worse at a task in terms of sample complexity. This is another landmark paper from the folks at MIT, What Can Neural Nets Reason About? And in this paper, they're actually able to prove a theorem which says that better algorithmic alignment, so basically better alignment of parts of your model with parts of your target algorithm, will lead to better generalization. You'll need fewer training data samples to learn such functions with those kinds of models. And in that same paper, they make the argument that graph neural networks algorithmically align to dynamic programming algorithms. Well, the fact I showed you Bellman-Ford was no surprise. In fact, this thing generalizes well beyond just the realm of Bellman-Ford. In fact, every dynamic programming algorithm, which, as you might know, cuts a problem up into subproblems, solves the subproblems, and then aggregates the results, also lines up very nicely with a computational graph. You can imagine each subproblem as a node in a graph, and then each subproblem computes its answer, and then the aggregation function aggregates the results from different subproblems. So there's something about the structure of message passing that lines up really nicely with dynamic programming. And it's something that obviously is a landmark framework for building computer science approaches. So this motivates even further why you might want to study graph neural networks in the context of algorithmic alignment. So now that we understand this, how can we make algorithmic alignment better? Well, the first thing you can do is modify the equations of the architecture, right? And, well, one thing you might immediately notice is the aggregation function of Bellman-Ford is the minimum. So why not make the aggregation function of the GNN something compatible with that, like max, right? And the reason why I choose max rather than min is because I combine it with ReLUs, and minimums of ReLUs will just lead to a bunch of zeros, right? So max might be a better choice, and it's symmetric to minimum, so it's fine. Just set it to max and achieve better out-of-distribution generalization on pathfinding tasks, right? I proposed this as early as iClear 2020, and at the time it was super controversial. For those of you who know some story about GNN expressive power papers, you might know that in traditional literature, max is seen as a really bad choice because there are proofs that it's strictly less expressive than averaging, which is strictly less expressive than sum over discrete features. However, I don't care about that kind of expressive power, which is really just about classifying non-isomorphic graphs. Two graphs can be totally non-isomorphic, and I can give them the same answer if they have the same shortest path. That's totally fine. Like, I don't care that they're non-isomorphic. I can give them exactly the same embedding. So at the time, this was a really controversial decision, but now with the ideas of linear algorithmic alignment, we can actually justify this decision very easily, because if you put a max in here, now suddenly the message function your model needs to learn is linear, so a ReLU MLP will fit it much better also out of distribution when it goes into the pure linear regime. Whereas if you put a sum aggregation in your GNN to fit this function, it can still learn it, but it has to now learn a highly nonlinear function of your distance variables and weights, such that when you apply sum to it, it will give you something that's like max, right? So it's really tricky and much harder to generalize. Fun fact, we use this exact same idea in our work with top mathematicians, where we help them analyze mathematical objects in representation theory, which led to our work that was on the cover of Nature and also was published in some math journals. It was the same idea. The mathematician told us about a target algorithm that he believed would help us solve the mathematical problem, and we built our architecture to algorithmically align to the steps of that algorithm. Another thing you can do, which might seem obvious, but it is an important direction to consider, is you could also modify your features to make extrapolation easier. And this was first spotted in tasks involving physics simulation, so n-body physics, like the interaction network paper of Pete Battaglia and others. So where you have to model interactions between particles. And as you probably know from physics, most forces that you might need to take into account here follow an inverse square law. So the electrostatic force, the gravity force, they all have a 1 over r squared factor in there somewhere. So you might imagine, because forces are basically the messages you need to compute between your particles, if you put just the distance as your edge feature, your message function is now nonlinear in those features because you have to compute 1 divided by r squared, right? And this will generalize worse. However, if you put 1 divided by r squared, or something that will tell you basically the square, the inverse square of the distance in your edges, now suddenly the force you have to compute is a linear function of your features, and you've done a bit of feature hacking to make extrapolation a lot easier. It's a very simple observation, but something that works remarkably well, and there's a great theoretical foundation behind why this is a good idea. Another one, which I really like, and we'll talk about this more in a bit, is we might also just want to constrain the architecture in some way. So we find some mathematical property that an algorithm satisfies, and then we constrain our neural network to respect that property. One beautiful example I always give for this is iter-GNNs from Haotang and others that was published at NeurIPS a few years back. And they noticed that most algorithms, including shortest path algorithms, have this nice homogeneity property, where if you multiply all of your inputs with a scalar, you get the same output just multiplied with a scalar. So if you multiply all the edge weights in a shortest path finding problem, you'll still get exactly the same shortest paths, just the distances are going to be multiplied by lambda, right? So you might want your GNN to compute a homogeneous function like this. And actually, the part in a ReLU MLP that makes it non-homogeneous is the addition of the affine term, the bias vector. So the only thing they did in this work is they took a standard GNN and they removed all of the bias vectors from the message function. And that's it. They removed that. And this model was already better at generalizing better on pathfinding problems. So sometimes it's really simple things, but they satisfy these mathematical properties well. And the last thing you could also think of doing is rewiring the computation graph itself, so the graph over which you're passing messages. As you probably know, in algorithms, we have many classical data structures that allow information to flow through those objects much more efficiently. Here is just one standard example. If you want to have a model that detects whether there exist paths between nodes in a graph, you can easily end up in these wacky situations where you have a long path graph and you might need linear time to solve this, even with the GNN. But you might know from computer science, we can organize our edges in a different data structure, the disjoint set union, where answering these queries are almost constant time in an amortized sense. The exact complexity is the inverse Ackermann function, which is less than 5 for all meaningful values of n. So let's recap what are all the things I've tried to modify in the past, or other people have tried to modify in the past, to make networks better aligned with certain types of computation. We modified, obviously, the parametric parts, the psi and the phi. We modified the aggregation function. We set it to max or something like this. We modified the features going into the GNN. And we also modified the computation graph, which is here expressed by the neighborhoods that you're doing the aggregation over. So you might wonder, what else is there to do to this equation? Have we exhausted the list of things that can be done to this equation? Well, it turns out we missed one thing that wasn't even in the equation, and that is the actual clock, the time steps of which we give you these input features and output features for a layer. So there's always an implicit assumption that the features are perfectly synchronized, and that at every step you have features at time t feeding in to compute at the end the output at time t plus 1. So we assume that there is a clock in here that synchronizes all of this message passing to happen all at once in all the nodes at the same time. But this is an assumption we might want to reconsider. So what I'm betting on is reconciling these GNNs, or just generally neural nets, with the concept of asynchrony. So maybe we might benefit from not being purely synchronous. And why is this important? Well, as we discussed at the beginning, we tend to struggle with both GNNs and transformers when we want to reason, especially out of distribution, especially over very long trajectories. And I think there is here a fundamental roadblock. There's just a function of the problem you're solving, not of the alignment to algorithms or anything like that. Sometimes to solve a problem, you cannot update all of your variables all at once, basically, right? Like sometimes you can only meaningfully update a subset of your variables and then use that information to update next variables and so on. If you're doing any kind of flood filling algorithm, right? You start from your source node and you have to fill its immediate neighbors, then its immediate neighbors, and so on. But there is an order you must follow, and there isn't any way in which you can influence a node that's super far away before you get information from nodes that are closer, right? And this is a fundamental topological constraint of the problem. And what's a problem when you then take a model that is synchronous and apply it to a problem like this? Well, you're being opportunistic. You're trying to update a variable ahead of time, and this is prone to failures. But all of the models we use, GNNs, transformers, all of our frontier models are fully synchronous. They update all the nodes or tokens everywhere all the time. So think about what will be the right message functions and update functions to do this fully accurately out of distribution, right? It will be like a bunch of identity functions for most nodes, but then for certain special nodes, you need to learn a highly complex function. I hope you can see how this is really tricky to learn in a way that will generalize outside of the training sets distribution in a robust way, right? And I said at the beginning, I care a lot about robustness. So how can we reconcile GNNs with asynchrony? Well, there's been a lot of relatively recent works by myself and a few other groups that have tried to address this issue. One work that I've done together with Valerie Engelmeyer and Dobre Georgiev tried to just say, okay, if GNNs are better at modeling synchronous algorithms, let's just try to make the target algorithm as parallel as possible. That's simple, right? It's elegant, scalable. We can theoretically prove that it's a good idea, but obviously it's not always possible. Not all algorithms are embarrassingly parallel, so we cannot do this at all times. Then there's a lot of body of work of saying, okay, we need asynchrony. Let's try to explicitly build GNNs that send messages at different times and don't explicitly synchronize. And some of the landmark work in this direction actually happened at ETH in Rod Wattenhofer's group in his collaboration with Lucas Faber, which was published at Log last year. And that's one of the first examples of an asynchronous GNN where you can send messages around from different layers at different times, and it's completely mixed. But they were able to prove that this already gives you higher theoretical capability. Then there's other works like cooperative GNNs, which in parallel were developed by Michael Bronstein's group at Oxford, where you have nodes that make their own decisions on, do I listen to messages right now? Do I send messages right now? And that determines the computation graph in each particular step. Now, this obviously directly solves the problem, but it's hard to scale. Like, I cannot scale this on modern hardware very easily. And there are many discrete decisions you have to make, like which messages are sent, am I listening, am I broadcasting? And these are all things that get tricky to learn in a generalizable way, especially with gradient descent. So that leads us to what we did, asynchronous algorithmic alignment, which actually tries to build models that are still synchronous, so I can still scale them, but make them provably invariant under asynchrony. So the model will update all nodes at once, but I can prove to myself that even if I randomize the order of the messages, I would still get exactly the same embeddings at the end. So this is a rigid mathematical constraint, which obviously results in a highly specialized model, but one that will be more resistant to asynchrony and therefore better at out-of-distribution scenarios because it's better suited for that. And this hits a sweet spot between being mathematically sound, so there's a mathematical background behind it, scalability, it's fully parallel, so I can scale it, and feasibility, it's something we can actually build. There are certain instances we've already been able to construct. So what we actually developed, that's the last part of what I want to say, asynchronous algorithmic alignment. So the general strategy will be is that we'll describe several levels of asynchrony we might want our model to support. And then at each level, we'll remove certain points of synchronization that a clock was necessary to be used for in a GNN. And then whenever we remove that, we'll try to put some constraints on the parts of the GNN, like the message function, the aggregator, or so on, such that it is still robust to asynchrony. And satisfying these constraints will give us asynchronously algorithmically aligned GNNs. So what we need to describe, there are three different types of data here that we need to talk about to kind of have a mathematical framework of what's going on. We have a set of all messages in flight, that's M. We have a set of all states that are in the nodes. And we have a set of all inputs to the message function, M, S, and A. In reality, you can think of all three of these as just k-dimensional real vectors, but I'm deliberately keeping them separate so that it's very easy to delimit which one came from where. Okay? And further, we want to assume that the messages and the arguments admit a monoidal structure. This is for a very good reason. Monoids are groups without inverses. They're a great abstraction to study just general purpose computation. And there exist exact correspondences between monoid actions and state machines, which makes us more happy that they're a good abstraction for something that you can basically write on a computer. In essence, what this means is that we mean that both messages and arguments to the message function can be iteratively assembled on the fly as data comes in. This is very important because when we asynchronize the whole thing, we will need to start assembling things from parts, right? So we need to be able to support that. And by the way, I'm very bullish on monoids. I think they're going to be really, really important. And that's why, for those of you who follow me on Twitter, you will know that in my bio, I recently put the word monoids, just to emphasize how important this is to me. And we'll write these two monoids as one of them being multiplicative and one of them being additive, but this doesn't mean that this is literally plus and times. This is just to keep two distinct monoidal structures in there, and they might be equal or identical, actually. And once I have now a message, which is an element of M, how does it act on a node state? So when a message is received at a node that has a particular state, it transforms the state, and it also transforms the argument. So it emits an argument to potentially send a new message based on that new state, right? And you have these two operators, the dot and the delta, which tell you once a message hits a state, what's the new state, and what's the argument that's being emitted to potentially send a message in response to that, right? Now, I'll keep this equation in the corner just so you have it in the back of your minds as we go through this. And we're interested in what happens when multiple messages arrive. So, because if we have asynchrony, it means that these messages can act separately or simultaneously, and we should achieve the same result in both. And this will imply a form of asynchrony invariance. So specifically, in order for this to work for state transformation, so the first part of this equation, we want this to be a valid monoidal action. So we want the act of a unit message to not transform the state, and the act of a composition of two messages to be the same as just acting with the first one and then acting with the second one, right? So this is what these two transformations mean. Neutral one doesn't change state, and you can either transform with two messages separately or first compose one and then the other. And for the argument emission, you have a slightly different rule, which is if you are acting on the state with a unit message, there's no messages to be produced in response. So this will emit a 0 argument. And if you act with two messages, you can either compose them and then act on the state, or you can first act with the first message, emit an argument, then act with the second message on the state transformed by the first message and emit an argument. And the combination of those two arguments, remember plus is the monoidal plus for those particular argument space, is the same, right? So these are the two equations that we need our model to satisfy. And by the way, this condition here is very popular in mathematics. It's known under many names. One, co-cycles, derivations, because they're related to the Leibniz rule of integration, and crossed homomorphisms, because they talk about the relationship between two monoids. And you can also imagine similar constraints placed on message computation. So once you have arguments computed, they can then be immediately shipped to produce new messages. But this is a stateless monoid transformation, because we typically assume that edges don't keep persistent state. And if they do, our framework actually would treat them as nodes, not as edges. So edges are something that carries messages and nothing else. So assume we have a special case of just a message with a single argument. So psi only takes the sender node features and produces messages. And to make this psi a cocycle, now it is the same equation as here, only we assume it's stateless. So there's no state input in any of these things. So what we have is that the effect of having a 0 argument produces a unit message. And if we have two different arguments, we can either first assemble them and then compute a message, or send two different messages for the two different arguments we produced, and then compose those two messages when they arrive in the receiver node, right? This, by the way, generalizes if you have a message function of multiple arguments. It's just that you then need your psi to be a monoid multimorphism rather than a monoid homomorphism. And this is a more complicated rule, so I'm just deliberately writing it this way to keep the maths a bit more simple. So what we then actually took and built is asynchronous algorithmic alignment in GNNs using these rules, right? So this is all the different points where GNN needs to block for different messages to arrive, and we might want to unblock that. So you have blocking on all messages arriving. Then when all messages arrive, you block on having the update function called. And then you block after that to compute a message, because you need all updates to be processed before messages can be sent, right? So first, to unblock the ordering in which messages are aggregated, that's actually unblocked in most GNNs already. All you have to do is basically make your monoid commutative, so such that the order in which messages arrive doesn't change the final aggregated message. And actually, in most GNNs, you use commutative monoid for the aggregator anyway, so this is totally fine. Most GNNs actually support this level 1 of asynchrony. We have a nice paper on learnable commutative monoids that we published at Log last year if you want some more details. And so this already, just using a commutative monoid, most GNNs are actually level 1 asynchrony aligned, and now we can kind of deharmonize the order in which these messages are arriving at the far end of the diagram. But we still have to wait for all messages to come before we can call the phi function. Now, to call the phi function asynchronously, we need the state changes, which is basically calling the phi function, to follow these monoid action axioms that we showed before. So this is what this looks like in the context of GNNs. Hopefully this makes sense, especially the second rule. So if I have two different messages, m and n, arriving to my node, I can either wait for them to be aggregated, then call my phi function on that, or I can first call phi on the first message, then use the result to call phi on the second message. I should get the same results, right? There's many ways to solve this. The one specific way we used in our paper is to set phi to be the same as your aggregator function, and then just leverage the associativity property of the aggregator to kind of naturally support this equation. So now you have that level, but also remember, we need to support asynchrony in how arguments are generated. So you need the second collection of co-cycle conditions to be satisfied. And I won't go into the details of how this works, but basically one way to satisfy it, you can see more details in the paper, is as long as your message state and argument spaces are the same and your plus and times monoid operations are the same, then as long as your update function is idempotent, this will work. So if we already set phi to be equal to O plus, as long as we set that to max, which is an idempotent function, you can apply it many times and still get the same outcome, this will work. This is totally fine. So now we have this max GNN, basically, right? We set phi to be equal to the aggregator, and we set both of them to be equal to max. This now allows us to call the update function immediately whenever a new message arrives. We still have to wait on all the messages to be processed before we can send new messages. But this is already a huge desynchronizer. Like, this allows our model, even though it's fully synchronous, to be invariant to a huge degree of asynchrony. This is like basically a permutation of all of your messages. For the final level, we need the message function to satisfy the monoid homomorphism rules. And here they are, just translated into message space. So basically, if I first take my two arguments, my two node states, and compute their max, which is our update function, then calling a message on that, that is the same as if I first call the message on the first one, call the message after the second one, and then aggregated them together using my max aggregator. As long as this holds, we can send messages as soon as we want and whenever we want for however many times we want. But to satisfy this, our message function needs to be not just any linear layer, it needs to be a tropical linear layer in the max semiring. What does this mean? This is basically a standard matrix multiplication still, but we're changing our times to be plus and our plus to be max. So this allows us, if we have our linear layer look like that, then it will work. It's worthy to take a step back and see what this tropical linear layer does. For those of you who come from computer science, you might already know that shortest pathfinding can be expressed by repeated matrix multiplication inside this max plus semiring. And here we're just having a learnable weight matrix multiplied with our high dimensional vectors in every node in this semiring. So basically what this model is doing is it's solving several tiny pathfinding problems inside the neural network architecture, each one of them starting from different instance conditions. And I don't think it can get more neurosymbolic than this, but it's still learnable with gradient descent. Well, not quite, because our weight matrix has quadratically many parameters, but because now our plus becomes max, only linearly many of them will actually receive gradients, because only one of them will survive the multiplication phase. As a quick fix to make it play with gradient descent, we use log sum exp, which is a semiring that's a smooth approximation of max. So as long as we have this message function satisfying a particular homomorphism constraint in the max plus semiring linear transform, for example, now you can call a message whenever you want in your layer, and it will still give you exactly the same answer as if you did it synchronously. So in practice, this leads to sparse gradients, so we use log sum exp as just an approximation. And this is now full asynchrony. And as you build GNNs that gradually ascend the ladder of this asynchrony, you have red as level 1, green as level 2, and blue as the full tropical log sum exp linear layers. You get better performance and out of distribution modeling of the various algorithms inside CLRS30. You can see their names at the bottom of the x-axis. So these are 30 different algorithms, from pathfinding to sorting to string matching to geometry. And you can see how generally, as you ascend this this ladder, you get better performance modeling these algorithms out of distribution. So it's worthwhile discussing that there's many points of future work, and I've left a few ideas here. We're exploring several of these, but if you have any ideas or are interested, I can feed back to this slide later if you want. I'd be very happy to collaborate. If you want to know more about any of this, there's a lot of points about neural algorithmic reasoning and algorithmic alignment I couldn't cover today because I wanted to focus on the monoids. We have a Log 2022 tutorial, which is 3 hours long, has public talks on YouTube, code of how to work with CLRS30, full slides, and a detailed list of references. So if you want to learn more about that stuff, check out this tutorial. If you come from combinatorial optimization and you want to learn more about how these models can be applied to learn problems that are NP hard, so much more complicated than polynomial time algorithms, we've written a 61-page survey on GNNs for combinatorial optimization that was published at JMLR last year. And section 3.3 specifically talks about the kind of stuff we discussed here. And lastly, the idea of removing constraints from groups towards monoids to make better analysis of neural networks. It's a hint at a much richer picture that's based on category theory. And we recently wrote a detailed position paper outlining this picture, and it's accessible on categoricaldeeplearning.com. Feedback is very much welcome. And actually, we take these one co-cycle conditions, and in the appendix of this paper, we rediscover them using the basic gadgets of categorical deep learning. Or as Mikhail Galkin put it in his meme that he put on Twitter, there is always a more generic theory that you can use, but categorical deep learning seems to be the one that's eating all of the other ones. So that's my last slide. Thank you very much. Sorry I went a little bit over time, and I'm looking forward to answering your questions. Thank you.
Thank you a lot for the amazing talk, Petar. I will take this moment right now to make an advertisement for the BCast happening in 2 weeks. On the 4th of April, we will have Peter Dubin from ECMWF, and he's going to talk about the digital revolution of Earth system modeling. Now we move to the Q&A session. You can either raise your hand and I'll unmute you, or you can write your question in the chat and I'll repeat them. So the first question I have is, so the reason why GNNs are very popular in R is actually the algorithmic alignment and the fact that they are dynamic programmers. But I have a question about one of the last slides where you mention NP hard problems. Do you also, what do you think? Do you also think that GNNs are worth exploring there, or neural architecture search is our only hope if we actually do not know the structure of the problem?
Right. So this is a great question, and we actually discussed it at length inside our survey papers. So reading that will tell you a lot more about our opinions. But what I can say in brief is definitely not. You cannot use GNNs in NP hard problems if you want to use them to solve the hardest instances of that problem under the same supervised learning framework that we were using here for polynomial time algorithms. The reason is because there's a very nice paper at ICML a few years back that basically says that it's impossible. It has a very nice title. It's not what machines can learn, it's what we cannot teach. Unless MP and co-NP are the same, which is very unlikely, that's a stronger statement than P equals MP. Unless they're the same, you can never sample a good enough data set to learn an NP hard function with a GNN or any other neural network in a supervised learning manner, right? So what does this leave us? Well, there's two approaches. Either you can consider things like unsupervised learning or reinforcement learning, which don't have those constraints, or you can wrap GNNs inside a more complicated algorithmic solver as an oracle function. DeepMind has done this in the past. Well, they wrapped the GNN inside a mixed integer program solver, and it was quite successful. So that's one thing that you can look into if you want. Another thing you might want, which is, I'd say, far more close, is that often you don't want to solve the NP hard problem, right? You want to solve a real-world problem for which the NP hard problem is a good abstraction. But for many cases in algorithmics, to reach those worst-case examples that push you into exponential land, you need to be adversarial, and nature is often not adversarial. The TSP has been solved for almost all cities on the earth, right? And actually, you have some algorithms like the simplex algorithm that are very efficient in practice. They are exponential time for linear programming, but all those cases where you get exponential time, you can always have a small epsilon, which pushes them into polynomial time territory. So you have to be basically deliberately sabotaging to find an adversarial example to push them into the worst case territory. So I would argue for most real world problems, even though they can be described using an NP-hard analogy, you don't really need to solve the NP-hard problem to do what you need to do. So in those cases, obviously a GNN would still be applicable.
Okay, thank you for the answer. Next question we have from Torsten. So everybody is focusing on making transformers very fast now. How do these optimizations impact your work on GNNs? Their sparse structure may not be the fastest as they're more powerful, as you mentioned.
Oh, yes, of course. So basically, I mentioned there's a few things we can do to the model to align it better to algorithms. And often one of the things we might not know, by the way, is what's the optimal way to pass data inside the algorithm itself. Like that depends on implementation sometimes, right? So what we actually often do in CLRS by default is we use a fully connected graph structure anyway. So we allow all pairs of nodes to communicate rather than just ones that would be connected by a list edge or something like this. This is particularly important for sorting, right? You don't always want to swap two adjacent elements inside your list. You might want to swap things that are far away, right? So we deliberately use a fully connected graph, which is conveniently exactly the same graph structure that transformers use. So you can use basically dense matrix products, much like a transformer does. And if you want to use a simpler update rule to like a transformer one, you can use it. So basically, these optimizations should hopefully not impact what we do because we're working with fully connected graph anyway, most of the stuff that we do. But I do agree that generally we might need better hardware for sparsity in the future. Like this is a completely separate point. And sometimes, like as problems get larger and larger, obviously the complexity of transformers and the generalization ability of them will diminish. And for that, we did some recent work with expander graphs that shows that you can stay sparse, but still very well communicative and scalable in these models. And for those systems, it might be very worthwhile to consider, sparse computation hardware. But for now, for what we do, it's not a problem.
Thank you. Next question we have from Maciej. The current development towards more powerful LLMs is based on making the models larger, more capable, but also simultaneously integrating them with the whole ecosystem of tools. Humans also do use tools, smiley, and the reasoning schemes, chain of thought, tree of thoughts, graph of thoughts, etc. How would you comment on these developments in relation to your approach based on more elaborate GNNs?
Yeah, my comment is actually quite simple. Like all these things are important. I think I said at the beginning, I think the ultimate architecture, the final thing in the end, will definitely use tools, will definitely use reasoning schemes, but the model itself will also be better at doing the tool-like things. So my comment is, I only use GNNs because they're an embarrassingly general model, and transformers are not general enough. They have a similar structure to GNNs, but they're not generic enough. They cannot represent everything. There are known papers that show that even the dot product attention already weakens the transformer. You can do more elaborate forms of attention that are stronger than that in terms of expressive power. So GNNs are there just so I can take into account every possible layer that I might want to encounter. But in reality, a lot of the ideas that we're designing here, we're very interested to just deploy them inside transformers, right? So that's another thing that we can do. So the fact that I use a GNN as my framework doesn't stop me from taking an idea that I found in a GNN and then deploying it in a transformer. I hope that answers your question, Maciej.
Okay, thank you. And I have one more question. So at one point during the presentation, you mentioned that one approach is adjusting the features. Do you think that we can actually incorporate domain knowledge during the learning? Because in the CLRS benchmark, the learning is based on the trajectory of the execution of the algorithm, for example, sorting. But do you think that we can benefit actually from the pseudocode or exactly the code that generated those things? Because now there are those LLMs that have some knowledge of the structure of the code.
Right. So CLRS as itself, I mean, it's built as a way to benchmark out of distribution generalization. I must stress that. So if you ask an LLM to solve these things, most likely it will produce code, which will produce correct answer. Well, sometimes, not always. I've seen them fail even on CLRS instances, to be honest. But there's a simple code. It's all over GitHub. The point of this game is not to produce good code, basically. The whole point is, can you learn a function, a very well-defined function, in a way that it will work even if I give you inputs that are far away, right? It just gives us a robust benchmarking environment to test that. But in a way to keep it robust and not confounded, we want basically the base models themselves to become more capable, not the models with tools, right? So we're deliberately not considering tools in the analyses and comparisons we do here, because that would be a confounder. You can solve all these problems very easily with a tool. In an ideal world, I would argue you cannot actually always solve them even with a tool with today's systems. But anyway, like multiplication, for example, still tricky sometimes if the system doesn't know to invoke the tool. So basically, I would say all of these things definitely help you solve tasks like these. And as I said, they'll be part of the final solution for sure, as I said in my response to Maciej. Here I'm doing it mainly because I want a better base model, which I can then hook up to that tool, so that when I get a complicated problem for which even extracting the inputs for the tool requires some kind of reasoning, I can be a bit more certain that my network is not going to hallucinate like crazy, right? So this is really the name of the game. But yeah, tools will definitely help with reasoning. I am not denying that. And algorithmic reasoning, the way we're currently setting it up, can be often trivially solved with tools. But this is not what we're trying to do, basically.
Okay, thank you. I think that is all from the questions. There are no more in chat, and I don't see any raised hands.
All right. Thank you. I mean, thank you for having me, and I hope you enjoyed it. Happy to talk more. You have my email on the slide, so please feel free to reach out at any point.
Thank you for coming.